Hello, everyone. Welcome to this session. We have Dr. Rohin Shah here to talk to us about why generalization is maybe more important than utility functions. So Rohin is a research scientist on the technical AGI safety team at DeepMind. And before that, he finished his PhD at the Center for Human Compatible AI at Berkeley. And Rohin is also the author of the excellent alignment newsletter. So without further ado, welcome, Rohin.
Thanks a lot, Beth. Yeah, so when I was giving my talk proposal, I thought this was going to be a more low-key conference than it actually is. So I, took the thoughts that were going through my head that particular week. I was like, I'll make a talk out of this. And that's what has resulted. So, maybe in 3 months' time, I'll be like, nah, that was not actually a great idea, and walk it all back. So, take all of this with a bunch of grains of salt. But anyway, so, as a result, this definitely doesn't reflect the opinions of DeepMind. It probably doesn't even reflect the opinions of like the DeepMind safety team. I'm sure there will be plenty of people on the safety team who would disagree with some of the things I'm saying. Okay, so let's get into it. Before I make my actual claim, I'm going to talk about the setting, the assumptions that I'm making. So the first assumption is going to be that we are going to get super intelligent AI via deep learning. I'm not going to argue for this, just going to assume it. So in particular, our super intelligent AI system is going to be this neural net, and it's sort of the computation instantiated by the weights of the parameters in the neural net that is super intelligent. It's not the training process, not gradient descent, that's super intelligent. Obviously, you'd still need a training process to train the AI system, but it's the end result of that is the super intelligent thing. And so you could imagine that this gets created in a few ways. So maybe you use DeepRL. So in this case, you've got an agent and an environment. The neural net is the agent. The environment provides some observations and rewards, and the agent acts on the environment, trying to maximize its rewards. So this was the technique used in AlphaGo and in OpenAI 5, for example. Another way that you might get the sort of neural net type AGI would be by training it on language. So you might ask it, hey, can you predict what word goes next in the sentence, drawing from a large data set of sentences that people have typed, I guess, online. And this is how GPT-3 was trained. And obviously, these particular examples are not super intelligent AI in the sense that we usually mean it yet. But the idea is if you scale up your neural nets enough, make your data sets large enough and varied enough, maybe this could lead to super intelligent AI. There's a lot more to be said about that, but I'm not going to get into it right now. Okay, second assumption is that we're going to have task-based AI systems, which basically means that we're going to be focusing on AI systems that are trying to solve specific concrete tasks like scheduling calendar events, rather than AI systems that are generically optimizing for human values. We might build those at some point, but those aren't, those are probably far further off in the future, not the first systems that will be risky. And I'm mostly not thinking about them in this talk. And so a canonical example of a task would be here's this calendar scheduling agent. Bob might ask his agent, hey, I'd like to hang out with Alice. Please schedule that for me. And so then the agent is like, yes, I know Bob likes to do this sort of thing on the weekend. And then maybe talks to Alice's scheduling agent and figures out when they're both free and schedules it for Sunday, April 7th or something like that. Yeah, so that's the second assumption. Third assumption is that there will be some form of distributional shift. So what does this mean? I'm taking a rather broad stance here. It's basically that there is going to be some difference between the situations an AI system is trained for and the ones that it encounters after it is deployed to act in the real world. And I have a very broad notion here. If the AI system, after being deployed, gains a lot of power and then is able to take over the world, and that's when it decides to take over the world, that counts as a difference between the training situations and the deployment situations because the agent gained a bunch of power in between those. And obviously the world itself is also changing frequently and constantly. So that also usually counts as a distributional shift. So this, I would say, is a fairly uncontroversial assumption. Perhaps more controversial part is the claim that any AI alignment solution will need to handle this sort of difference. And so as a canonical example that you can think of, we've got our scheduling agent. It was trained to create scheduling events in sort of normal situations. And at deployment, a pandemic hits. This agent was trained in 2019, we say. Pandemic hits in 2020. And now when Bob says, I want to hang out with Alice, presumably he means I want to have a video call with Alice. And the agent might even know this. The agent could be intelligent enough to know that Bob really wants a video call with Alice. But during training, it was always, rewarded when it created an event at a bar for Alice and Bob to hang out. So maybe it just continues doing that. That's a way that an agent might fail under distributional shift. Similarly, a treacherous turn when the agent gains a lot of power. That during deployment, that also would count as a distributional shift. And then that could lead it to take over the world. And so, I give you this example not as an example of existential risk. It's obviously not an existential risk, but sort of more as a concrete example to keep in mind that's like easier to reason about for the rest of the talk. Okay, so we've talked about our three assumptions, which were, just to recap, that we'll get powerful AI systems via deep learning, they will be task-based AI systems, and that distributional shift will happen and we need to handle it. So under those three assumptions, my key claim is that we should be using generalization guarantees rather than utility functions to reason about distributional shift. A claim I am not making, I'm not saying utility functions are useless. I do think you probably still want to be thinking about them, but the sort of like overarching theme of like what you like the final guarantee that you should be thinking of getting with your AI alignment solution should be about generalization rather than what is the utility function that the AI is optimizing. Cool. So what do I mean by a generalization guarantee? Basically, you sort of want to produce two guarantees for any AI system. One is what we might think of as the capabilities guarantee. It's that in training situations, in normal situations that the AI has already encountered, we see strong performance. It like actually does what its designer intended it to do. In this case, it schedules events correctly. And then the second guarantee we would like to make is that at deployment, it at least generalizes acceptably. Maybe it doesn't schedule events perfectly, but it's not going to do something that's totally crazy. It's not going to become so misaligned with us that it's trying to seize power from us or kill us all or something like that. So in the example of the calendar scheduling agent, it might be that like when Bob says, I want to hang out with Alice, and the agent knows that now there's COVID, everyone's in quarantine, then it would not be acceptable if the agent, continued to schedule an event at a bar. It would be acceptable to schedule a video call, which would be the correct, the nicest possible behavior. But it would also be acceptable to say something like, all right, I know COVID's happened now. What should I do in response to that? How should I change my behavior? That's also acceptable. Yeah. So that's sort of the generalization guarantee way of thinking about what we want to do in AI alignment. In contrast, the utility function one, it's not so obvious. So before I go into why that is, just some caveats on this. In this talk, when I say utility, it's synonymous with reward, goal, objective, all those other words that sort of mean the same thing. Some of my audience is probably thinking, oh, but those are actually different concepts. They do in fact refer to different things. And I agree that there are multiple concepts that sort of all fit in this general bucket, and I'm going to now talk about sort of all of them and why I don't think any one of them is all that useful for thinking about generalization and distributional shift. So the first thing you could try to do is have a behavioral utility function. This basically means you take your agent, you take the training data, you look at how the agent behaves on the training data, and you say, hey, what does it look like the agent is doing here? What is it trying to optimize for? And so you find a utility function U that sort of rationalizes the agent's behavior, explains the agent's behavior. And the main problem with this is that it doesn't really tell you much about what the agent's going to do in deployment. In particular, there can just be many utility functions that are consistent with the training data, but make different predictions under distributional shift. So for our scheduling agent, for example, it's consistent, its training behavior is consistent with the utility function, do the thing that Bob wants you to do or be helpful to Bob. But it's also consistent with when Bob says to hang out with Alice, schedule an event at a bar, regardless of whether there's a pandemic going on. And so like those two utility functions are both consistent with the training data, but make very different predictions about what the agent will do in the case where a pandemic is actually raging. Another way of saying this is like if we choose a specific utility function according to this, we don't really have a good reason to expect that it predicts correctly under distributional shift. So one thing you might say is like, okay, well, clearly our problem was that we're only looking at the training behavior. Let's just look at all the behavior. So then we'll require that our utility function U explains the agent's behavior on all possible inputs rather than just the training, just the inputs seen at training. And the problem with this, there are a few of them. One is that it's sort of hard to apply to humans. Like we're constantly debating the meaning of life. So it's not like we don't really know what a human's behavioral utility function is. But sort of more fundamentally, it's sort of, if you take all of the agent's possible behavior and you then find a utility function that rationalizes it, in some sense, that utility function is just sort of a re-encoding of the policy. Like you knew all the behavior, and then you have a utility function, and that also lets you know all of the behavior, but you sort of knew all the behavior already in order to come up with the utility function. So you haven't really gained anything. One thing that you might try to do is say, okay, I'm not going to encode the sort of entire policy. I'm going to like correct for biases and mistakes and stuff like that. And then that will give me a sense of like what the agent is trying to do. But unfortunately, then it's like, it just seems quite hard to do this. And like, it's not clear how you're going to define what's a bias versus what's a weird preference that the agent has. This point is basically the same as the second point, just stated differently, is that, you know, if you only get your utility function by knowing how the agent behaves in all possible situations, it's unclear how you benefit from getting the utility function. If you know the agent's behavior in all possible situations, you're done. You know whether or not it's safe. Yeah. So maybe the problem was that we were sort of like trying to rationalize the agent's behavior in some situations. And instead of that, what we should be doing is like looking for the things that drive the agent's behavior rather than like trying to rationalize it after the fact. So I call these structural utility functions. And an outer structural utility function is the thing that drives the agent's performance that's embedded in the training process or outside the agent. So for example, in deep reinforcement learning, we've got our environment, in this case, DOTA, a reward function, like +1 for a win, -1 for a loss. We've got the sort of actions, observations, rewards. And then we just say, we draw a circle around the reward function and say that thing over there is our utility function. The biggest problem with this sort of utility function is that it just doesn't matter in the deployment what the values of the reward function are in under distributional shift. The agent only ever sees rewards on the training inputs, the training data. Excuse me. And you know, if our if like when we like made the reward function for a scheduling agent, we made sure that like, in the case where a pandemic has hit, we'll make sure that the reward is high if the agent schedules video calls instead of bars. But then during training, the agent never sees the reward values for when a pandemic is hit. You haven't gained anything. It doesn't affect the agent at all. So like getting this right under distributional shift is just not very helpful. And so you don't really want to use this to reason about distributional shift. There's another slight problem, which is that like as a concept, it's often unclear what does and doesn't count as part of this utility function. I can give some examples afterwards, but for due to time constraints, I think I'll just move on. Cool. So one thing you might say is like, all right, well, the problem is the sort of reward function goes away once you get to the deployment, setting where distributional shift happens. What if we instead search inside the agent for a reward function or utility function, which will still be there during deployment? And so that's an inner structural utility function. And the way we might formalize this is to make an assumption about the agent, which is that the neural net, the weights of the neural net are implementing some sort of search or planning algorithm that, considers possible situations or outcomes or plans or actions, and then ranks them according to some metric of goodness, and then like does an argmax to find the best one. And then we like figure out what the metric of goodness is, and we say that thing is the utility function. If you're familiar with MESA optimization, this is just a description of a MESA objective. If you're not, don't worry about it. The main problem with this is, if you interpret the assumption strictly or literally, I just don't expect it to be true. I don't think neural nets are going to be learning explicit search or planning algorithms. I can talk more about that offline. You might think that, maybe we can try and have some sort of looser interpretation. Like it's not literally a search or planning algorithm, but it's still like sort of, it like thinks about consequences, it will sort of weighs them against each other, that like determines its action somehow. And we can still get a metric of goodness out of there. And this could work out. I'm not confident that it won't or anything like that. It just seems hard. It seems very vague right now. And I don't feel very optimistic about that vagueness going away. And also it seems likely that if you have to sort of have a loose interpretation of the assumption, then the utility function becomes less defined. And there could be many possible utility functions that are compatible with the definition. And once again, they might make different predictions, as in the case with behavioral utility functions on training data. So those are, 4 different kinds of utility functions, and why I don't like any of them for reasoning about distributional shift. And that is why, I claim currently, tentatively, I might not claim this in 6 months from now, that we should be sort of at the top level trying to get generalization guarantees rather than trying to embed utility functions inside of AI systems, especially when we're reasoning about distributional shift. Thanks.
We have about 5 minutes for questions. So ML as a field has been trying to bound neural network generalization error for a while without that much success. How tractable do you think getting strong generalization guarantees are?
Yeah. So I think that the sort of standard work from statistical learning theory on generalization bounds is not exactly the thing that I mean, because a lot of it assumes that there isn't any distributional shift. And then a lot of it says that there might be distributional shift, but there's like a finite or something like finite set of hypotheses, set of possible models. And those sorts of assumptions usually aren't true for neural networks. So I think that sort of assumption, those sort of guarantees basically won't work. I'm not that optimistic about theory in general being able to give these sorts of guarantees. it seems like you need to be making some sort of assumption about how reality is. Like there are a bunch of empirical results in deep learning where like neural nets can memorize randomly labeled data, but then when they have correctly labeled data, they still like learn the right function that generalizes reasonably well, despite the fact that they could have learned like literally randomly labeled data. So it seems like there's some property of reality being simple that we don't really know how to formalize such that we could write theorems about it. So I'm not very optimistic about that. I think I'm more optimistic about more heuristic reasoning, like instead of training AI systems to just optimize for the right outcomes, let's try to select for AI systems that get the right outcomes for the right reasons. So like, peer into the reasoning of the network using perhaps interpretability tools or something like that. And that lets us select for AI systems that are going to generalize better. So I sort of see this sort of generalization guarantee as more like defining what we're trying to do rather than how we're going to do it.
Right, yeah, because to me it's not clear why the agent doing things in the right way is different from like it has the right structural utility function or something. Or could you explain the difference between those?
Yeah. So I think there's like a sort of weak notion of utility function or objective or goal, which is like, the agent's sort of generally trying to be helpful when it does its reasoning, it like, excuse me, thinks about what the human wants and then like figures out a way to help the human get that. And if you have this sort of very, very, very loose notion of what an objective or a goal is, then I'm like, sure, we can think of it as like, it's like a slightly narrower conception of, it's like one specific way to achieve a generalization guarantee, but it does seem like, the most likely way that you would get something like that. So yeah, so I guess my answer is like, yeah, for like a sufficiently loose interpretation of the word objective, I would agree with that. It does, but I would like pretty strongly recommend not trying to make it more formal, because when you do, you sort of run into the problems that I've been illustrating in this talk.
Cool. So someone asks, so with the behavioral utility function definition, can we maybe solve the problem by distinguishing between the utility functions that are just like a different representation of the policy versus utility functions that compress the agent of the policy a
lot? Yeah, so Stuart Armstrong and Soren Minderman have a paper on this, which basically shows that at least under Kolmogorov complexity, this doesn't work. And the reason for that is like, well, I should not try to explain this in 30 seconds. But suffice it to say that people have tried this. It does not actually work. I refer you to the paper's name, I believe, is Occam's razor is insufficient to infer preferences. And then there's, I think, a subtitle as well, something like that.